Alright folks, welcome back. This is video number 4 here, and we've done all the setup. We're ready now to begin the iterative part. We're going to jump inside the self-consistent field loop here, beginning with step 5, coming from the 12-step algorithm on page 146. So let's get started. We've done a lot of setup. We're ready to really start doing things here. So step 5, we're going to boost our iteration up to 0. Let's make sure we actually do this. And then we're going to calculate the G matrix using equation 3.154 in Szabo and Osland. The G matrix is kind of the effective potential and electron fields, kind of the smushed out average of all the other electrons in the system. It's not very exciting the first time around because you remember our initial guess for the density matrix was to fill it up with zeros, so the G matrix is going to be 0 as well. So not very exciting the first time around, but that'll change later, but it should be 0 now since we started with a 0 density matrix. So we'll move on now to step 6. And step 6, we will add our G matrix, our effective part of the electron interactions, to the core Hamiltonian that we calculated back in step 2. So it's easy to do that. Nice doing that in Mathematica because it knows we're dealing with matrices. So I just say F equals H core plus G, and then we have it. Ta-da! We have our Fock matrix. That's the first time we've seen it. We now have the Fock matrix. So there it is. It's the same as the core Hamiltonian at this point, but we've gone through the calculation. And according to Szabo and Osland, this is when we want to do a calculation of the electronic energy. So I've put in equation 3.274 to calculate the electronic energy at this point. And this is so as we proceed through the algorithm, we can start replicating the numbers that we see in table 3.5. So we'll look at this value later, but we've got it now to look at later. So with that done, we'll move on to step 7. And step 7, we're going to calculate the transform Fock matrix. We're going to take the Fock matrix we got and then transform it into a orthogonal basis so we can solve what kind of sort of look like an eigenvalue equation. We eliminate the problem introduced by the overlap matrix in the Rutan equations. This will eliminate that so it can be solved as a something that looks kind of like an eigenvalue problem. So we'll do that using our X matrix that we calculated back in step 2, our transforming matrix. We'll calculate the adjunct by just taking the transpose, and then we'll have it. We have our F prime, as they call it, using equation 3.177, going through the change of basis process here of X dagger Fx. So that's done for us. It's ready to go now. From that we can calculate the coefficients in the transformed orthogonal basis. So we'll move on now to the next step, step 8. Yes, I can calculate the coefficients. I can calculate like a C1 prime and a C2 prime. And this is more of a chemist thing than a math thing, but you get two sets of coefficients. You get a C1, C2. Ultimately, we'll get a C1, C2 for bonding and a C1, C2 for anti-bonding. But step 8 here gives us the coefficients in the transformed orthogonal basis, which isn't exactly what we want, but it's a step along the way. So that's step 8. We'll use our familiar 1.105 to calculate this. Our C prime here is calculated in the same way as the, what do we call it, the U matrix back in step 3. So we'll calculate that the same way, and then we'll calculate C prime the same way as well, using 1.104. So this gives us our coefficients. It's actually a very big step we made here. We have the coefficients, we just don't have them in the real world basis, but we'll take care of that in step 9 here. Okay, so step 9, we'll calculate the coefficients in our basis as opposed to the orthogonal basis. So we'll do that using our change of basis formula, x multiplied by c prime, which is equation 3.174 in the textbook. So yeah, it's done. I mean, that's really it. That completes the calculations we need here. After this is all done, after we've converged, it should agree with 3.275. But we haven't converged yet. We're a long ways from convergence. So let's just move on at this point. We need to form a new density matrix. We'll use equation 3.145. We now have calculated orbitals, so we can now calculate a new density matrix based off of those orbitals. So there it is, our P nu, we'll call it. P nu will replace P. And let's see, I'm getting behind here. I'm failing to execute these things. Let me go back and run these so we can see them. Now these values that come out here are our value for the Fock matrix first time around, or our value for the transformed Fock matrix first time around. These values should agree with values you find in the textbook. Okay, so there we are. There's our new P matrix. Remember, we started off with a guess of saying it's all 0. Now that I've calculated it, it's not 0 anymore. It's made a big change. The density matrix has changed a lot here. So it's just showing how far we are from convergence at this point. But it's good. We've gone one time through. Let's open up step 11, which is the last step within the algorithm, within the iterative part of the algorithm. 11 just kind of checks, have we converged yet? Has P changed? Well, yeah, it really has changed. It was zeros to begin with, and now it's got a 1.72 and a 0.259, so it's made a big change. I'm using a formula that's not numbered in the textbook, but it's found on the top of page 149 for monitoring convergence, basically just calculating. It's based on the difference of P and P nu. So calculating that, I'm going to call it delta. And let's see what we got here. Pretty big error. Our delta value is 0.88. So we're a whole long ways away from convergence. Electronic energy is 0 at this point. But that's okay. We've made one pass through. I'm going to stop the video here, and when we come back, we'll go back and we'll run this until convergence. I'll go back to step 5 and we'll run through it again, and then we'll watch how these values change as we march towards convergence. So thank you for watching. I'll see you back in video 5 when we will do some iterative loops here. Goodbye.